All right, so I'll go ahead and start.
So just in case I need power, I just want to make sure I find it here.
There should be an outlet or a power strip underneath the table. You'd have to open the door behind the console. It's not on the front side. It's on the other side.
Is there power?
Oh, yeah, it's way back.
It would be on the other side. There's a door on the other side of the console.
Yeah, it's on this side, right?
The back side.
The back side.
The side facing the audience.
Okay, let's take a look.
Yes, that door right there.
There we go. Outlet. Oh, now we have
No, there's one here.
Unplug
There's
something.
one here.
No, there's
Yeah,
there's
but this is not going to fit in there.
Should be. Yeah.
Let's not unplug anything.
Okay, brilliant. Yeah, that's what I was worried about. Okay, perfect. Okay, I think I'm ready to go. Please go ahead.
All right, go ahead, sir. We're recording.
Great. It's our great pleasure to have Dr. Peyman Milanfar here. Dr. Milanfar got his bachelor degree from UC Berkeley and master and PhD from MIT. From 1999 to 2014, he was a professor of EE at UC Santa Cruz. And from 2010 and 12, he was Associate Dean for Research at the School of Engineering at UC Santa Cruz. From 2012 and 2014, he was on leave at the Google X, where he helped develop the imaging pipeline for Google Glass. Okay. And now he leads the computational imaging and image processing team in Google Research. He holds 10 US patents, and some of them are commercially licensed. And he's a 2016 IEEE Distinguished Lecturer for IEEE Signal Processing Society. And as you can see from our flyer, and he also won several Best Paper awards. And he's a fellow of IEEE. So today he's going to give a talk on image processing with graph Laplacian operator. Let's welcome our speaker.
Thank you very much for the nice introduction. It's a pleasure to be here. I know this is lunchtime, so I won't dive in with equations. Also, feel free to interrupt me at any point. I'm happy to answer questions in the middle of the talk. So I want to start with a couple of anecdotes to give you a bit of perspective about why image processing is difficult and so important these days. So this is a statistic that I certainly, for one, wasn't aware of before I started working at Google, the scale at which things happen. So more than 2 billion photos are shared on social media every day. It seems like an astonishing number. If you divide that out, that turns out to be about 23,000 images a second. Right? So think about that. That's like a speed at which a scientific high-speed camera would work. Right? Maybe even more astonishing than this is over 100 million of these images are selfies. And that's something like 1,200 selfies per second. Right? And when I put these slides together, this particular slide together, this was maybe 2 or 3 months ago, and I'm sure these numbers are even bigger now than they were back then. So we have entered an era of, modern era of easy photography. Here's what we do, or at least the younger ones do. Take a picture, do something to it, and immediately share it. The message almost is that it's almost as if the picture isn't for you. You're taking the picture for somebody else. Because you take it and you almost immediately share it, and then you forget about it. So the reason I bring this up is because things have to be done. If you're doing image processing at scale, in a place like where we are, you have to do it fast and you have to do it effectively all the time. So let's go back for a second and give you some perspective. How did we get here? Back in the very early days of consumer photography, you would buy a roll of 12 exposures. It would cost you an arm and a leg. And you would really be careful in terms of how you took those shots. You would take the 12 shots, and maybe 6 of them were really awesome. Right? And then a few years went by, and the film got a little cheaper. So you had 36 exposures. You took a little less care, and still only 6 of them were awesome. Now you have a memory card where you can fit several thousand photos, and still only 6 of them are awesome. Okay? This said, this 6 could be any of the 2,000 that you took, which means that if you're doing image processing, you have a hard problem to solve now. You have to do well, you have to do it rapidly, and you have to do it at scale. And those are the things that are important in sort of the marketplace of visual data nowadays. OK, so this is my sort of 2-minute summary of perspective that I wanted to share with you. Now let's move on to some more technical side of things. So whenever we process images, one of the very basic operations that we engage in is called filtering. And that filtering is simply taking an input-out image. This doesn't show anything on the screen, does it? OK. All right, well, I'll point then. You take an input image, and you map it to an output image, let's say of the same size. There are various versions of this where you can take an image and produce a bigger image or a smaller image, et cetera. But let's stick to this one. OK, same size. And the operation that you generally do is you take the pixels from the input image, some set of pixels from the input image, combine them with some weights, and you map them to a pixel in the output image. And you repeat this process for all the pixels, or some subset of the pixels that you're interested in changing. OK, now, if you look across all the applications, like getting rid of noise, getting rid of blur, making things sharper, better, et cetera, each of these filters for each of those applications is something completely different. So each case where we design a filter, it's sort of like a designer filter, hence the Gucci symbol here on the filter box that I put. OK, so that's one characteristic. Filters are designed very, very specifically, very carefully for each application. And the second characteristic is that we've evolved from having filters where the weights are fixed to filters where the weights change depending on the input pixels. So when the weights are fixed, these can be simple convolution filters, for example. Same filter is applied everywhere in the image. Nowadays, we've moved to an area, or to an era, I should say, where the filter weights change. And I'll say a little bit more about that in a minute. OK, so here's an example. Let's say I take this input image, I map it to this output image with a constant weights, which are a Gaussian kernel everywhere. So each patch gets convolved with a Gaussian like this, and this is the output. You're just affecting a constant blur across the image. We've now graduated to more fancy things where the weights are now depend on the underlying pixels. In what way? So suppose you want to process this pixel, and you want to get rid of noise on either side of this edge. Well, you don't want to change the edge. You want to keep the edge still sharp. So if you're sitting somewhere right on this edge, just to the left of the edge, then you come up with weights that look like a Gaussian on this side, and they're effectively 0 on the other side. What does that mean? It means a pixel right in the middle here is averaged with all the pixels that look like it, and it is not averaged with pixels that don't look like it. OK? These are called spatially adaptive weights for filtering. So the kernel shape depends on the image content. Exactly how, we'll talk about that as we go on. So an example of this, by the way, is bilateral filter, non-local means filter. So has everybody heard of bilateral filter? OK. All right. So now let's describe a little bit more precisely the mathematics behind these kinds of filters. So let's say, like I said, I have all the input pixels and all the output pixels. Let me call the input pixels y, call the output pixels z. Here's the relationship between one output pixel and possibly all the input pixels. And I can take all the weights that correspond to that pixel I, and I can put them in a vector, right? And this is the vector. Then I can take all the weights for all the pixels and stack them into a matrix like this. OK? So now I have a relationship between the input pixels and the output pixels that is a matrix vector multiplication. Now this looks like a simple linear filter, And if the weights W don't depend on Y, then it is, in fact, exactly a linear filter. If the weight depends on Y, then it's a pseudo-linear filter. It has the structure of a linear filter because it's just a matrix vector multiply. But you can do things in two stages. Stage 1, you take the input image, you compute the weights in this fancy way. Stage 2, you take the weights and you multiply them by the image. Okay? Not every filter can be written this way, but almost every filter can. Okay, so it's a very, very wide and natural way of describing these filters. Okay, so now, so let me give you some idea. These Z's and Y are the image values stacked into a really long vector. So if you have an n by n image, the vector Y is n squared by 1. Vector Z is n squared by 1. And the matrix W is n squared by n squared. Okay? There's going to be an enormous an enormous matrix. We don't actually do the image processing this way. Too much memory, too much storage, etc. But it's a really good way of analyzing things. Okay. So what do these matrices W look like? If you have a filter that acts locally, if that mapping that I showed you from the input pixels to the output pixels is only using some of the pixels on the input to produce a pixel on the output, then many of the elements in the matrix W are going to be 0. Those are these big blue regions. Okay? Some of them are going to be 0. And those are here near the block along the diagonal that has non-zero elements in it. Right? If the support of the filters that you use on the input is a very large region that gets mapped to a single pixel, or the entire image possibly, then you have a matrix that looks like this. These are what we call global or non-local filters. Okay? What's the difference between these? Well, the difference, it turns out to be, is a very interesting one and maybe hadn't been noticed before. Matrices like this are sparse. Many of the elements are 0, but they tend to have high rank. Why? Just the intuition is that a matrix like this looks like a diagonal, right? Let's take it to an extreme. Suppose it is a diagonal. What's a rank of a diagonal matrix that has non-zero elements along the diagonal? Full rank, right? So the more close you get to this, the more full rank you get. It turns out these dense matrices that use pixels from everywhere in the image tend to have low rank. Why does that happen? Because images contain a lot of redundancy. If you take any given image, patches from this image look like many other patches in the same image. Take a picture of this room, right? The walls, the pictures here that I'm showing you. And pick a patch, pick a little region, and think about, are there other little regions in this picture that I just took that look like it? You will find many. And the reason that happens is because just in nature, and especially in man-made nature, buildings and so on and so forth, patterns repeat themselves. And so you have low rank. As you'll see later on, there's an advantage to using filters that have a large support because you have this low rank property. Okay. So now, this is the very basic groundwork. And now let me talk about Laplacian operators. Now what I'm going to do is I'm going to start from defining Laplacian operators from the very basic principles, most of which you probably already know. And I hope to convey some intuition that maybe you didn't have, and then go from that to the graph Laplacian, which is sort of the next version of the Laplacian that I want to talk about. So first, let's talk about the simple Laplacian operator. All of you have taken calculus. So I'm sure all of you have seen the Laplacian operator. It's basically the second derivative. If we think about a function with two variables, it's the second derivative of the function along each of the axes x1 and x2, summed together. This operator is all over physics. If you study any area of physics, you will see it pop up. And it turns out there's a good reason for it. I'll get to that momentarily. Heat equation, wave equation, Schrodinger's equations, Maxwell's equations, equations that describe fluid flow, they all involve this. Also, if you go to image processing, if you look at the literature in image processing, you will also see that the Laplacian operator is all over image processing as well. Well-known filters like anisotropic diffusion, curvature flow filters, adaptive sharpening filters, deblurring, etc., etc. These also all involve the Laplacian operator. Okay, so I gave you the very basic definition. Now let me give you some intuition about what the Laplacian operator is all about. So for the sake of simplicity, let me not worry about the two-dimensional case. Let's just talk about the one-dimensional case, in which case the Laplacian operator is simply the second derivative of a function. Okay? So now what I'm going to do is I will write a numerical approximation to the second derivative. And this is going to be using the central difference. Right? So you have, if you look in the denominator here, if you have 3 pixels next to each other, is a filter 1 minus 2 plus 1. Right? That's the second derivative operator. And then you divide it by epsilon squared because there's 2 derivatives going on there. And now I'm going to take this and I'm going to rearrange it ever so slightly. Namely, I'm going to do this. Okay? So a coefficient comes out 2 over epsilon squared. I have this term here, which looks like the average. It doesn't look like, it exactly is the average of z at x plus epsilon and z at x minus epsilon. And then I have z of x. Okay? Why did I do this? Because I wanted to show you that this term is the average of the function z around x. And this is the actual value of the function z at x. So what the Laplacian operator does, when you apply it to a function at a point, it measures how different the function is at that point to its average around that point. Okay? So this is the basic property. This is called the non-conformity property of the Laplacian operator. It measures difference between the center and its surrounding region. And we're going to try to generalize this. This general description that I just gave you also holds for the Laplacian described in d dimensions, Euclidean space. So this is the Laplacian. This here, exactly the same thing, except more general. 2d over some constant as a function of epsilon, d being the dimension. Again, you have the average minus the center. So the Laplacian operator, again, very generally speaking, is a center-surround difference. Okay, this thing, it turns out, shows up in an amazing place that gives you an idea of why it's so important in processing images. It actually shows up in your visual system, believe it or not. There is something, this notion of antagonistic receptive fields, which means that the way your eyes work is the rods and cones and the cells that receive light, they don't send their raw output to the brain and hope for the best. There's actually a lot of processing happens between the rods and cone signals and the optic nerve that sends the signals to the brain. And what happens there is very interesting. What you have is basically the cells, these ganglion cells here, will fire at a rate that is proportional to the center minus surround difference of the rods and cones responses. Okay? So really what your brain is getting is not a signal individually, but it's getting a signal through a Laplace operator applied to what the rods and cones are seeing. Okay? In fact, it's very interesting. They've done experiments. This is now well established that if you, the human vision system and also in all mammals, if you actually paralyze the muscles that move the eyes around, there is a process that is continuously ongoing called saccadic motion, where your eyes are never completely stable. Their eyes are constantly going like this. Even if you're staring at a single point of light, your eyes are going like this. If you paralyze the muscles that move the eyes, and the eyes really stop moving, you stop seeing. And the reason you stop seeing is because center surround don't change. Okay? Yeah?
Just want to get something clear. You're saying at a particular time, your nerves are sending differentials of stimulus?
That's correct.
Not in time. Like, it's not, we'll say, like, I'm getting this kind of photons after this movement will...
What I'm describing is at a particular time, this is what happens. What happens over time is not the point of discussion.
I see.
Right. Okay, so the other important thing to remember is that these cells don't respond linearly to the input. So in other words, the Laplacian that I just described to you is a linear Laplacian that doesn't depend on the data. It turns out that these cells have a nonlinear response to their input. And this will be the inspiration for us to define the next set of Laplacian filters that I will call the graph Laplacian. OK, so again, let's talk about the Laplacian properties a little bit more, just to summarize. As I said, it detects local non-conformity in the signal that it views. If you look at the Laplacian of a function being equal to 0 and then ask yourself, what is that function? It implies that the function is very smooth. OK, because think about what it means. It means that the function is equal to its average everywhere. Everywhere you go, the function value is equal to its average. So that has to mean that the function is somehow behaving in a very smooth way. And in fact, this is the definition for harmonic functions in harmonic analysis and analytic functions in complex variable theory. And what I just described is the mean value property. If the function is equal to its mean in nearby region, that's the mean value property. The other cool thing is that the Laplacian, a function that satisfies Laplacian of z equal to 0, is a minimizer of this cost function. If you take the gradient of z and look at its norm, and then integrate it over all the domain values, the function that gives you the smallest answer is the Laplacian. And this will turn out to be another very important concept. This energy, by the way, here, the energy of the gradient, is also referred to as the Dirichlet energy in the literature. OK, so now let's ask the question I just posed here. If this is the minimum, if this is to be minimized, we get this. Let's see, how do we get this? This is presumably the steady state solution to some evolution equation, right? So what is that evolution equation? It turns out that if we parameterize the function with a parameter t and assume that as t goes to infinity, we'll get Laplacian of z equals 0, then let's see what that evolution looks like. And we can get that by taking this function on the left, replacing z of x and t in it, and then computing a functional gradient descent. This is a gradient descent not in the numerical sense of gradient descent, but a functional gradient descent. In other words, what you're doing is you're going to perturb the function a little bit and then use that as the gradient of the functional, and then move one step in the direction of that gradient. Well, if you carry through the math there, what you get is this equation, which is called the diffusion equation, and you might also know it as the heat equation. OK? You start this with some value z0. And as this equation evolves, the solution that it gives you is called the heat kernel, which is just an exponential, which evolves to become more and more flat over time. So the solution of this equation is z0 convolved with a Gaussian. And the Gaussian is a function of space. And t is like the variance of the Gaussian. And as time goes to infinity, or as sigma goes to infinity, this gets flatter and flatter and flatter. OK? All right, so we've got the Laplacian. It minimizes the Dirichlet energy. And you can get to the solution by doing an evolution along this diffusion. OK, now I'm going to do something a little different than what I did before. Before, in order to give you the center surround property, I took the function and I wrote it as an approximation in x, right? Now, as a perturbation in x, I should say. Now what I'm going to do is I'm going to keep x fixed, and I'm going to perturb t. In other words, perturb the variance. And let's see what that does. OK, so if I take the left-hand side here, and I perturb this left-hand side as a function of t, this is what I get. This is sort of the derivative. It's a numerical approximation to that derivative. And then I know from this solution here that each of the z's is z0 convolved with a Gaussian. So I can write the left-hand side as z0 convolved with a Gaussian with parameter t plus delta t, and another Gaussian with parameter t. So two Gaussians, one with a variance that's a little bit bigger, and one with the variance that's just t. So the intuition I want to impart here is that the Laplacian can also be computed as the difference of smoothing operators. So you can take two functions that are Gaussian convolutions with a given function, subtract them from each other, and get an approximation to the Gaussian. This is also well known. If you've done image processing and you want to approximate a Laplacian, you know that you can do it by computing the Laplacian of Gaussian, right? And that's basically this, what I'm showing you. OK, now all of these things that I just laid down are going to come in handy later on when I get to the broader concepts. OK, so now I've talked about things kind of in the continuous domain. It's very useful for intuition. Let's go to the discrete cases, go back to the discrete cases that we discussed at the beginning, and see how things work. So I have an image. These images are generally defined with their pixels or patches of pixels. So from this image, I'm generally going to be looking at a patch, let's say like this. And these patches are going to be arranged as vectors into a vector z, right? And then if I want to filter the image, I'm going to multiply w with z. OK? So I want to make sure, so far, this is completely clear, I hope, right? I mean, I've said it probably too many times. All right, so this is a weighted average filter. The weights might be dependent on the data. OK, so now, what do I mean by the Laplacian? The Laplacian is simply the residual of applying the filter and the image. So you apply the image, apply a filter to an image, subtract it from the original image, and you just call that the Laplacian. It is not a ridiculous and arbitrary definition. It is a center-surround definition, right? You've got the pixels, and then you've got weighted average of the pixels, and you're subtracting them. So it's consistent with the general definition that we had before. OK. And so the main definition of the Laplacian that we're going to be working with is identity minus the filter matrix. OK? And this is the matrix that I'm going to call L for Laplacian. All right, so now we're finally ready to move on to the graph Laplacian. OK, so what is the graph Laplacian? Here, we take a slightly different view of what images are. Typically, you're given an image. What is it? It's just a collection of numbers. You stack it into a vector, OK? Collection of numbers still. What I want to do now is think about an image as nodes in a graph. It's not a complicated idea. Take every pixel, index it by I, and put it at a node in the graph. And then think about all the pixels that are connected to it as j. And when I say connected to it, I don't mean immediately its neighbors. This general notion of how connected things are is completely open to interpretation. You can imagine a pixel being connected to every other pixel in the image. OK? Seems like overkill, but hear me out. If you connect every pixel to every other pixel in the image, maybe they shouldn't be connected with the same weight, right? There's no reason that a pixel here and a pixel there should have any relation to each other necessarily. So what I'm going to do now is I'm going to turn this graph, which is heavily connected, is in fact fully connected. Everything is connected to everything. I'm going to weight these edges with a number kij for each pair I and j. And that kij is going to measure what I call affinity between two pixels. Affinity means similarity. So if two pixels are really similar to each other, this affinity would be high. If they're completely dissimilar, it would be low. Now, what do I mean by similar? I'll define that in a minute. Again, the notion of similarity is very general. You can say, OK, if two pixels are really close to each other in space, I'll call them similar. If they're close to each other in space and close to each other in gray value or color value, I'll call them close. Or you might say, I don't care how close they are in space. If they are far away in space, but they're close in the gray values or pixel values, I'll call them neighbors. Or I'll tell them I'll call them high affinity pair. OK? So this is how we do this. An example of it is this. I just mentioned it. If you take the spatial position xi and xj, you can say e to the minus the norm of xi minus xj, normalized by some smoothing factor. That could be the affinity between two pixels at I and j. Or the affinity could be just the pixel values differences. Or you could take these two Gaussians, multiply them by each other, and call that the affinity. If you just use this one, what you have is something like the Gaussian filter weights. If you use this one, what you have is called non-local means. If you use both of them, multiply them together, you have the bilateral filter, or bilateral kernel. I haven't mentioned how the kernel relates to the filter. I will in a moment. Okay? It turns out your choice of affinity is much, much broader. You can do many other things, but let's stick to these for now. Okay, what do these look like? So let's just take this kernel here, which measures similarity. And take these two pixels. One of them is kind of bluish here and the other one red on the dog image. And the values in the two images that I'm showing you here, the red values means high affinity. The blue values mean low affinity or low similarity. So here, this pixel has a lot of pixels that look like it, or at least the neighborhood looks like it. And this one, relatively few. Makes sense. That's a very particular kind of edge. Okay? So in terms of the matrices, if you were to think about K as a matrix, just like W was a very big matrix, this is the affinity matrix as opposed to the filter weight matrix. Each one of these, if you take them and stack them into a vector, would be one row in that affinity matrix. Okay? It's the affinity between a given pixel and all the other pixels. Okay. There is an interesting concept here, and these are all things that I'm slowly introducing from graph theory. If you take all the weights that point to a particular pixel, you give a pixel and look at all the weights that point to it, basically one row of this affinity matrix K, and sum all the values in that row. That gives you the sum total of all the affinities for all the pixels that point to one particular pixel, right? This notion is called the degree of a node in a graph. We'll call it the degree of a pixel. So it's a sum. You keep one of the indices fixed and you sum over the other one. And it looks something like this. So here what I've done is I've computed the D value for every pixel in the image here. Right? And remember, so basically the sum of the rows of the affinity matrix K, I've computed and put it over here. What does this tell you? In the deep red regions, it's telling you that pixels in this region are very similar to many other pixels in the image. And that makes sense if you look, for example, in this region, you're talking about all these blackish pixels here. And then the areas that are blue or light blue are more rare pixels because they have fewer friends. Okay? Not as much affinity with the other pixels. Okay, we'll use this number D in a significant way as we go in the next few slides. Okay, so finally, let's get to the graph Laplacian and define it. The Laplacian of a graph designed like this, at the pixel I, is a sum over Kij of the difference between Zi and Zj. So if I got rid of Zi and Zj, it would be sum of Kij would just be the D that I just showed you, right? So here, I'm putting the difference between the two pixels and summing. I can rewrite this a little bit. Zi here doesn't depend on the index over which I'm summing, so that comes out of the sum. This one doesn't, right? So I can write this as Zi times Di minus the weighted sum of the Zi's with these weights. Make sense? Okay. So the Laplacian is defined as follows. It's the pixel value times its degree minus the weighted average of quote-unquote its neighbors, in which case the neighbors are possibly all the other pixels in the image. Okay? I can write this in a somewhat more general way in a minute. Again, it has a center surround mean value property. It measures smoothness, just like the continuous case that I mentioned to you earlier. There's a notion of diffusion with this Laplacian. And in fact, a more technical result is that if there are enough pixels, if you like, enough data points, and things behave in a reasonable way, this converges to the continuous definition of a Laplacian, not in the Euclidean sense, but if you think about the space over which you're working is a manifold on which the image sits, then this notion actually converges to the continuous version of Laplacian on that manifold. Okay, so let's take this, and I'm going to write it in a slightly different way. So I'm going to take all these Z's and stack them into a vector again. These di's that multiplied, I'm going to put them into the diagonal of this matrix D. This is a diagonal matrix. Okay, so dz, elements of it are simply these guys. This weighted sum is just like the weighted sum I did with the w's, except that here there's k's. So this is a matrix K times Z, right? Okay? Now, here's the notion of smoothness. I said before, smoothness was implied by the Laplacian of Z being equal to 0. So let me let the Laplacian of Z be equal to 0, right? If you just solve this, what you get is Z equals D inverse KZ. And it turns out here's the connection between the weight matrix and the matrix K. D inverse K is the weight matrix that I showed you before. Okay? So the only difference between the weight matrices that I used and K is this normalization with a diagonal matrix. Why is it there? Intuition is very simple. When you do a weighted average with Z, you want the sum of the weights that you use to combine the pixels to sum to 1. Right? Otherwise, you're going to be changing the brightness value differently everywhere in the image, and your result is going to look ridiculous. Right? So because this guy is normalizing by the sum of the weights, this K is getting normalized by the sum of the weights in all the rows, which is this diagonal matrix. Okay? So W is equal to D inverse K. And if Z is equal to a filtered version of itself, you have smoothness. Right? So this is a really key concept that helps you understand why it's useful to use this Laplacian equal to 0, Laplacian of Z equal to 0, as a way of enforcing smoothness. What it says is that Zi, every pixel, is equal to a weighted average of the pixels, the rest of the pixels, with a normalization factor. Okay? And we can use this as a prior to enforce a fairly sophisticated version of smoothness. Okay. Okay, so any questions before I go on? Okay. All right, so now, how do Laplacians give rise to filters? I just showed you the very generic description of you've got an affinity matrix K, you normalize it with a diagonal, you get a weight matrix. More importantly, early on I showed you how minimizing the Dirichlet energy gave you the Laplacian operator on Z equal to 0. We can do the same thing here. Here, the Dirichlet energy is basically the same function that I showed you before, except that Zi minus Zj is squared. Okay? If you do a little bit of algebra, a little bit of manipulation, you can write this quantity as Z transpose LZ. It's just a quadratic form with the Laplacian in the middle. Okay? And by the way, this Laplacian, under the right condition, is symmetric positive definite. Its eigenvalues are between 0 and 1. It's got all these nice properties, but I won't mention those just in the interests of time. Okay, so you do Z transpose LZ. Now you ask yourself, how do I minimize this? Well, minimize it using gradient descent. Okay, start with a given image and do gradient descent on this thing. And what you get is zk plus 1 equals I minus L zk. And remember, I minus L is just W. So zk plus 1 is W times zk. If you just do one iteration of this, what do you get? Z hat equals Wi, which is the filter that I showed you. Okay? This also shows you that if you do more than one iteration, if you just keep going, increase k, this is the notion of diffusion. Diffusion here means that W just keeps getting raised to higher and higher power. Okay? Because W has eigenvalues between 0 and 1, what happens when you keep raising it to a higher and higher power, all the eigenvalues die except for 1. And that 1 turns out to be an eigenvalue which corresponds to an eigenvector, which is a constant image. So when you raise W to the kth power as k goes to infinity, you get a constant output, which is exactly what diffusion does in the continuous case, right? You diffuse something, it flattens out. Here, you diffuse this way on an image, you apply a filter again and again and again, you get a flat image back. Okay, so that's one way to do it. You just take this guy and just do gradient descent on it, you get your filter. Here's another way to do it, which may be more familiar to you. Suppose you have an image Y, and you don't want to just find a filter to just, boom, apply to it. You have a filter, you have a Y, and you want to write a term that looks kind of like this is the log likelihood, right? And this is a prior. Okay, it's a sort of standard optimization that you do. Okay, and so you want to minimize this term, but you want this result to sort of stay close to y. Well, if you carry gradient descent on this, you get a slightly different filter. You get zk plus 1 equals wzk. This is what was there before, right? Without that regularization term. I'm sorry, without that data term. This is what was there before. It was diffusion. Now you have this extra term. This thing is called the diffusion with source. So it's a diffusion, but the diffusion, it keeps getting additional information, which is the residual at each iteration. So it doesn't die out to a constant. You can also do this. Suppose you have a filter in mind, which is related to this w. You can say z minus wy. So z is not close to y. Z is close to wy. Do gradient descent on this. You get yet another kind of formula. Each one of these things, by the way, has been the subject of really, really good, very sophisticated papers. I'm just giving you kind of a 30-second summary of all of these things. So this thing is called SOS boosting. And finally, if you apply this Laplacian not to the image directly, but to the residuals, so you define this Dirichlet energy on y minus z as opposed to z itself, and then do gradient descent on this with this initial condition, you get something that is really old. There's this notion called boosting, or in the statistics literature, it was known as twicing. It was introduced by Tukey, who was a very, very famous statistician. You might also know him from the Tukey window in electrical engineering, the same guy, back in '77. What this says is very interesting. It says you update the image with the previous image plus a filtered version of the residuals. Now think about what you're doing. Give me a filter. I apply it to the image. Unless that filter has done a perfect job of, let's say, getting rid of noise, it has gotten rid of the noise plus some of the image, right? And so if I look at the residuals, these residuals contain not only noise, but some of the image that I wanted to keep, but which I wasn't able to do because my filter wasn't perfect. So what this does, it says, hey, this is not uninformative. I'm going to filter this yet again. It's like a rinse cycle, right? I'm going to put it through the filter again and add that here. Now, what do you think would happen if we kept going with this? If we just repeated this process, what would happen? We're adding high-frequency information back to the image again and again and again. The way you can see what happens is if you set k plus 1 equal to k and then solve, well, as k goes to infinity, k plus 1 and k are the same. The steady-state solution to this guy is just y. You start with y, you filter it, and if you keep doing this, at the end, at convergence, you'll get y back. Okay? So if you want to do some useful filtering for visual purposes and so on, you have to stop any of these iterations, you have to stop them at some point. It's useful to think about this after one iteration, actually, what happens. If you just said k equal to 1, you get 2I minus w times y. It's useful to interpret this. W times y is like a low-pass filter, right, smoothing, whereas I minus w is like a high-pass filter, like the Laplacian, right? So at each iteration, what this guy is doing is not just smoothing. It's doing a smoothing followed by sharpening. Okay? And then as you go, the effect of the smoothing dies out, and the effect of the sharpening goes up, and eventually you get the original image back. Okay, so there's all these other things that have been done with different names in different parts of the literature that are all basically the same thing. Okay. This whole business also gives you a really nice way of considering a kind of decomposition algebra for signals. So if you study signal processing, you know about taking a signal and decomposing it into Fourier components. If you've done a little bit more advanced stuff, you know about taking a signal and decomposing it into wavelet basis. Then related to wavelet basis are multiscale decompositions that are very popular, so on and so forth. So here's another decomposition. You take an image y, and you filter it two different ways. One is by w, and the other one is by I minus w. So the actual filter and its Laplacian version, right? Then you take this guy and decompose it again. Same way. Filter it with W, filter it with WY with the Laplacian again. Right? They keep going. Okay? Up to some level K. Why did I do this? Seems like a strange idea. Think about it. Along the left side, you're doing smoothing, and smoothing again, and smoothing again, and smoothing again. On the right side, you're treating the residuals. Right? High frequency stuff is coming out. Okay? Another way to think about it is the thing on the right, the path along the left is like a Gaussian pyramid, whereas the path on the right is like a Laplacian pyramid. Okay? What's the difference? The difference is that these filters W are not simple Gaussian filters. These are nonlinear filters, right? Like the bilateral filter or non-local means or any of these other things that you like, as long as they fit into this big structure. So what you're doing is you have a decomposition that looks very much like the ones that you've seen, except that the core filtering component is highly nonlinear. The other nice thing here is that this, by the way, for those of you with a mathematics background, these polynomials here that you see, if you look them up in the mathematics literature, they're called Bernstein polynomials. These are called decompositions of identity. Right? You take an identity. That's what I did here. This is the identity. You add these two, you get identity. And this is at least to my next point. You have this perfect reconstruction property from these decompositions. If you add these two, you get Y. If you add these three, you get Y. If you add these four, you get Y, and so on. Okay? So what does this tell you now? It tells you that if I want to take a signal and modify it in some way with some sophisticated filters, I have the option of taking a filter, designing it carefully, and applying it, or I have the option of taking that filter, decomposing the filter in this way, applying these, and then adding them together with different coefficients, right? And I get a much wider class of filters. Let me explain. So for example, this boosting that I just showed you earlier, I can take these three components and put these coefficients in front of them, and I can get this filter. Okay? Any polynomial here, I can span it by putting different coefficients in front of these guys. And in fact, any function that can be expanded into a polynomial can be treated this way. And this is not a very restricted case, because I have functions which are filters that are working on images which are numbers between 0 and 1, or 0 to 255 if you like, for an 8-bit image, right? So I have functions that are bounded on a compact interval. So I know that I can approximate them with a polynomial with a high degree of accuracy over that polynomial, right? It's the Weierstrass theorem. And because I can do that, this is very relevant. It's not just a niche idea. It's completely relevant to almost arbitrary filters. Okay, so here's what we do, in fact. If you want to process an image, this is how we think about these things. We build a bank of filters. The input image comes in, goes through these filters. You pick some arbitrary K. K actually doesn't have to be very high for you to get really sophisticated properties. And if you think about these, each of these terms, if I go back here, each of these terms looks like the difference of two smoothing operators, right? So this one is like W minus W squared. W squared is just W with the bandwidth a little bit different. Okay, so we pass this image to a bank of filters, use some coefficients in front of those, blend them together, and get the output. And that's what I've written here. So you can produce an output that's much more sophisticated than just one application of the filter. We can go one step further and say, okay, why do these W's have to be related in this very specific way? Now that I have WK and WK plus 1, I can think about the W's as simply being different filters that are in the right sense complementary to each other. Okay? And the choices of W1 and W2 are not going to be arbitrary, but I can define a class of W's that are sort of closed under the kind of operations that I'm describing here. And so here, I'm just writing these as components that are basically the differences of smoothing operators applied to the image and then blend it together. And then here, I'm just rewriting them as Laplacians. So one particular Laplacian with a particular parameter applied to y and others, and then summed together. OK? And again, so this is sort of obvious. Each one of these components is like, this is a smooth component, that first one. And then the other ones are just details. And then I'm choosing how to combine these details together. And the choice of the filter that's underlying it is very, very general. OK. So since we've come this far with kind of making use of the linear algebra properties, and this is all really I've used is linear algebra, let's take it one more step and think about linear embedding. I just mentioned it as in the previous couple of slides. So suppose that we wanted to, I talked about this notion of minimizing the Dirichlet energy, right? Now suppose I want to minimize the Dirichlet energy normalized Z transpose Z, right? This is equivalent to maximizing Z transpose WZ because L is simply I minus W, right? OK, so this should look familiar. Minimizing these normalized quadratic forms or maximizing, these are eigenvalue problems, right? And so what you get is if you minimize these things, maximize this or minimize that, what you can see is that the filtered image that you get at the end of the day is a linear combination of the top eigenvectors of W. I mean, in theory, it's a linear combination of all the eigenvectors, but you can chop them off at some point. So I can filter by simply taking W, doing an eigendecomposition on it, and then combine those eigenvectors with different coefficients and get an image. That's another way of looking at what I just showed you in the previous slide, which was passing things through banks of filters. Or equivalently, it's a linear combination of the bottom eigenvectors of L. Remember, the top eigenvectors of W are the bottom eigenvectors of L because it's 0, 1, switching over. OK, I can show you what these look like. Here's an image. This is the first eigenvector. Not very interesting. It's a constant. OK? Second, third, fourth, 5, 10, so on. So the earlier ones encode sort of piecewise constant regions. And then as you go, there's more and more detail in these. So if you combine them, you can get interesting filtering effects that are non-trivial because the filters that I use underneath are highly nonlinear. Or you can chop off the highest ones and just get denoising, for example. How many eigenvectors should you keep? Remember early on in the talk, I mentioned how the eigenvectors, sorry, I mentioned that the full matrices had low rank, right? This turns out to be very important here. If I look at the eigenvalues of these matrices, they decay extremely fast. So the picture that I showed you before, this is the first 10 eigenvalues from that picture. OK? So by the time you get to 10, they're almost 0. Now think about how big that image was. I think that image is something like 500 by 1,000 pixels or something like that, right? So you have hundreds of thousands of eigenvalues, but only like the first couple of dozen of them matter, right? So what that means is that if you just got your hands on those few eigenvectors, then you're in business. You can do really, really sophisticated image processing. There is a problem here that I'm glossing over, which is if you have the affinity matrix or the filter matrix, it's enormous, right? How do you do eigendecomposition on this thing? It's not easy if you just try to do it directly. It's not even easy to hold that matrix in memory. However, what we end up doing is we sample that matrix. And with very few samples, it turns out you can get your hands on the top eigenvectors. In fact, you need on the order of m samples to get the first m eigenvectors. We sample the rows of that matrix, I should say. And it's really a remarkable result. The reason that happens is because the matrix is numerically low rank, so you can get away with that. OK, just to put this in a different picture, this would be the filter, right? In this kind of low-dimensional embedding, this matrix W turns into something like this. These long rectangular things are the eigenvectors. There's only a few of them. So you project Z into these subspaces like this. And then you adjust the coefficient in this little matrix, and then you project back out. Okay? And that's all there is to it. There's a bunch of different definitions of the Laplacian that are not exactly the one that I just mentioned here. Was there a question? No? Okay. So the definition of the Laplacian I mentioned, I don't want to leave you with the impression that that's the only way to define the Laplacian. There are others, and so I want to mention a couple of them. This was the definition of the Laplacian that I gave you, right? D minus k. Now, earlier, I defined the Laplacian as being related to I minus w, right? And I also defined w as d inverse k, right? So what gives? I just gave you two different definitions of the Laplacian. One of them was d minus k, and the other one is I minus d inverse k. Well, the only difference between those two is whether you divide by this di or not. If you don't divide by di, this is the definition of the Laplacian. If you do divide by di, then this becomes d inverse d minus d inverse k, which is identity minus d inverse k. And it turns out that's also a perfectly valid definition of the Laplacian. That diagonal term is a scaling that one can deal with. Both of those Laplacians, and in fact these other ones, have very much similar properties. The things that we care about in terms of the definition of the Laplacian is the range of the eigenvalues, which we can fix. So these are the two definitions that I gave you, I minus d inverse k and then d minus k. Okay? And by just normalizing this, we can get the spectral range also fixed. Okay, so let me just skip over this in the interest of time. So these are the two I just mentioned. It turns out I can make them equivalent by just putting an alpha in front of this guy and then letting alpha be 1 over n, which is the size of the pixels. This is the effect if you just apply a filter defined by one kind of Laplacian versus if you define the filter with a different kind of Laplacian. They look very much similar. Right? One of them is slightly weaker in terms of how much smoothing it does. These are the residuals. Okay, so again, in the interest of time, this is very quickly, it's a data term here and regularization. We can also do deblurring. It's basically the same formulation except that I've thrown in a blur here. We can solve problems like this. Again, regularizing with the Laplacian. So this is one example. The student that did this just graduated. Really nice piece of work. If in this situation you let A be equal to identity, so you don't have the blur, you just say it's identity, then what you get is something that looks like effectively a nonlinear unsharp mask. So if you apply this nonlinear unsharp mask, you can get some very interesting effects. So the image from the left is the starting image. The image on the right is the one you end up with. This is not deblurring. This is smart sharpening. So basically what the filter does is at each point it figures out how sharp the image already is and how much it needs to sharpen it, and it gives you this back without having any knowledge of the point spread function that affected the image. So just a few more examples and we're done. One example, so we've applied, by the way, all of these techniques that I mentioned to you in one form or another are applied in the work that we do in my team. Many of these algorithms, as I've shown them to you and as these examples show, actually already run on devices, right? On Nexus phone or on an Android phone. They already run. So they're not just sort of mathematical niceties. They have practical use. Low light imaging. You start with an image like this, and you don't like the way it looks, you want to brighten it, right? If you just take an image like this and brighten it, what you'll see is that these dark regions are noisy, and if you brighten it, it gets even more noisy. So we designed filters that will brighten the image without making the noise in these areas worse. So they're simultaneously doing denoising and contrast enhancement to good effect. So this is a detail from the same thing. Okay, so here's another one. This is a totally different example. Same set of filters, just different parameters, different tuning. Dehazing. This is a hazy picture of this bridge. This is so before and after. So again, this is before, and this is after. This is a little more subtle. This is here we're actually increasing the dynamic range. These pictures were taken through this glass enclosure that the cupcakes are in. So this is before and after. And now look closer. Before and after. Okay, so we can get rid of garbage that's kind of in between you and your subject to some extent by doing this. This is a high dynamic range tone mapping. You take an image like this, the sun is in your field of view, you want to be able to see everything else really well, so we can do things like this without blowing up the noise. This is another example. This is in the Stanford Chapel, so it's kind of like turning on the lights, right, without making the noise worse. Another example. We can do compression artifact removal, for instance. So again, this is before and after. And again, I want to emphasize these are all the same sets of filters, just different configurations, solving all these different problems. Noise-aware sharpening and contrast enhancement. So again, before and after. OK, I think I'll stop here. Thank you. Happy to answer any questions.
Time for questions.
What is the interpretation of the parameter h in that kernel function? So you have
What is the interpretation of the h in the kernel function? Right. So the h is basically what's called the smoothing parameter in the kernel function. If you so imagine if you look at the affinity function, right? The affinity function is e to the minus an exponential divided by h. So if you set h to be a very large number, what happens is that you get e to the minus a very large number, right? And so the affinity becomes the same for everything, right? On the other hand, if you make h really small, you're making more of a discrimination between the affinity for different pixels. So depending on how much you increase or decrease h, you're kind of deciding how much you want to emphasize the affinity between pixels.
like how many dominant eigenvectors you want to choose.
Oh, you mean in terms of the eigenvectors? Yes, yes, right. So if you set h to be a very large number, then your affinity matrix is just going to be all ones, right? And then you don't have more than one eigenvector, right? So that's a good point. The value of h that we set will affect the rate at which these eigenvalues drop. So we set the value of h that you would set for doing regular filtering, right? You wouldn't set h to be a really large number. Otherwise, you're just doing box filtering, right? So what I didn't say was that for the particular values of h that are practical for filtering, the eigenvalues decay in this particular way. Make sense? Okay. There's another question?
A couple, I was interested, firstly, whether this filter bank includes edge decompositions as well as region decompositions.
Right, so as you go through the higher and higher order eigenvectors, then you see very strong edge preferences. It is not in the classic sense, so you know, there are decompositions that are with steerable filters that are that respond to particular directions. These don't really work exactly in that way because the filters are not really built to be direction sensitive necessarily. So if you look at the affinities are simply looking at differences of pixels, right? Sorry, go ahead. So those differences are not necessarily including or encoding specific directional information in them. You could imagine changing the affinity function so that it is not just computing the difference between two pixels, the difference between two patches. It is also taking into account the shape of those patches in a kind of higher order way. But we haven't done that here.
I was wondering when the low rank versus dense approach, Richard Bach-Bert looked at whether you do or do not want the loadings of the low rank component to themselves be sparse.
Yeah, that's an interesting question. We haven't really thought about that too much. I know kind of on the theoretical side there's been some interest in this. On the low rank question, by the way, this is a question that I don't really have a proof for. I mean, I mentioned that several people have worked on it, and there's optimality results in terms of decomposing into the eigenvalue space. But why is it that the affinity matrix for natural images tends to have low rank for reasonable values of h is an open question, right? So there may be a much deeper question underlying this. It's reminded us of you know, several, I don't know, 2 or 3 decades ago, there was a lot of work on statistics of natural images, right? If you look at the power spectrum of natural images, they decay at a particular frequency. It's like 1 over f squared type of thing. And I think this low rankness has something to do with that, except that this is kind of at the patch level, whereas that was at the pixel level. So it's a high order statistical property of natural images, apparently. Yeah. Other questions? Yeah. The what collection?
Can you push on her when you ask the question, please?
Yeah, so it's a collection of artistic filters.
Oh, the NIC collection.
Yeah.
NIK,
Yeah, just wonder, like, from a designing perspective, how would you come up with, designing the graph that would achieve, your artistic effects? I mean, do you know?
Right. So a couple of things. First, I should say I was not involved in the NIC filter. That was done in a completely different team, and it was done before I joined Google. But it's a good question. I mean, you can say to yourself, I have a really nice collection of filters that I can offer people, and what subset of them or what set of them will span the most interesting artistic effects? I don't know. I don't know what the answer is to that. So far, the filters that have been selected and floated to the top in terms of options for things tend to be things that people are interested in. I mean, who would have guessed, for example, if you look a few years back when Instagram first came out, just a bunch of simple filters, right? Nobody in our community, I think, would have guessed how big it would become. So it's really hard to predict what people will like. I don't have a very good answer for you.
Do you have any general references for this? Maybe last question.
As a matter of fact, I do. That first one is a review paper that I wrote a couple of years ago, and then the other ones are sort of more detailed. I'll share the slides with Hamid and the organizers.
Slides will be available.
Yeah, so you can get the slides and also feel free to email me, and I can. This is my website. All this stuff is on my website. So if you just go over here, mylastname.org, everything is there.
So in the interest of time, maybe we'll have to stop here. So let's thank our speaker again.
Thank you.
I'm actually intrigued by that random one filter that you showed.